As we did with 2-degree of freedom systems, with multi-degree of freedom systems, we can find closed-form solutions when we have free, undamped vibration. We can identify free, undamped vibration in multi-degree of freedom systems when we put our equations of motion into matrix form, and it comes out in the form of mx double dot plus kx equals 0. And this form looks exactly the same as it did for 2 degrees of freedom. However, now that stiffness matrix K and the mass matrix M are going to be more than 2 dimensions. They're going to be larger than 2 by 2. And then the 0 vector on the right-hand side will have as many zeros as we have degrees of freedom in our system. So when we have this as our matrix form equation of motion, we know that we are going to get the general solution for x of t to be the summation of ci chi I cosine omega it plus phi I. And we see that the general solution for a multi-degree of freedom system is just a more general form than we had for the 2-degree of freedom. We're going to have as many of these c's and phi's as we have degrees of freedom in our system. And we see that all these variables have the same interpretation as they had for 2 degrees of freedom. We have as many natural frequencies as we have degrees of freedom, as many mode shapes as degrees of freedom, and we're going to have 2 times the number of degrees of freedom in constants, the c's and the phi's, those amplitudes and those phase shifts. But we're also going to have 2n initial conditions. So we simply add more and more cosine terms the more degrees of freedom we have in the system. And the way we're going to be finding these constants is pretty much exactly the same as we had when we had 2 degrees of freedom. So for example, to find the natural frequencies of our system, we're still going to take m inverse times k, and we're going to find the eigenvalues of that. The square root of those eigenvalues are going to be the natural frequencies of our system. The only difference being m and k are going to be larger. So at least by hand, trying to invert that matrix M and multiply it and then find the eigenvectors and eigenvalues is going to become more challenging. However, since we're typically going to be using something like MATLAB or Mathematica to find eigenvalues, eigenvectors, it's just going to take a little bit longer for it to run. Going onwards to the mode shape, same idea as for 2 degrees of freedom. The mode shapes are just the eigenvectors of that m inverse k matrix. So we could solve them by hand, but again, the larger our system becomes, the more cumbersome it's going to become to try to do this step by hand. So once again, using something like MATLAB is going to make finding those mode shapes much easier. One thing we want to take particular attention to, especially as we get more and more degrees of freedom, more and more natural frequencies, is that we're paying attention that each mode shape is associated with one of our natural frequencies. So if we were to sort our natural frequencies in ascending order, which we usually should, we want to make sure that it is still associated with the same mode shape if we change the order. So at this point we can find our natural frequencies, our mode shapes. So the last step, like we saw for 2 degrees of freedom, is to get that total solution where we're going to be applying our initial conditions. So these are what the displacements are going to look like for all of our degrees of freedom, and then the velocities, just taking the time derivative of the summation term. And as we saw, we can apply our 2 times the number of degrees of freedom initial conditions to find these constants, these c terms and these phi terms. Now, a difference at this point is going to be how we did it for a 2 degree of freedom system, where we could basically use a solver, an fmin search, or an f0 to solve those, at that time, 4 unknowns, 2 c's and 2 phi values. This process is going to become much more complicated if we keep adding more and more degrees of freedom and keep upping the number of initial conditions that we have. So instead of using that fmin search to solve for these, we are going to be using principal coordinate analysis, which we'll cover later in this section. But we're going to see that as we get more and more degrees of freedom, especially as we get to doing finite element analysis, where we could have hundreds or thousands of degrees of freedom in our system, the principal coordinate analysis is going to be a much more efficient way to find all of these c's and phi values.